with the next one as well, the mechanisms are long, but in my opinion, some of the steps are a little bit easier. Okay? And they're easier steps because you're looking at acid-base reactions. So it's put on a hydrogen, take off a hydrogen, put on another hydrogen, take off another hydrogen. Okay? So mechanistically, if you go through and look at sapling, you have to then evaluate each and every single one of those steps, which is definitely tedious, and you have to do it in the proper order, but that's how the mechanism is supposed to officially be drawn. Okay? So what we're going to go through and do is work our way through this mechanism first, which is kind of what we ended with, and I talked through it really, really fast last week, and we didn't actually look at all the individual steps. Okay? So we'll look at this first, then kind of finish up chapter 20, and probably get into 22 just a little bit. At least that's what I hope, because that's where we got a quiz. Okay? So to start off, what kind of conditions do you think we're looking at here? Acid or base catalyzed? Why acid catalyzed? Yeah, our oxygen is protonated. I don't like these lights. Our oxygen is protonated. So if we take a look at our starting oxygen, it's already been pre-activated. Okay. What does that additional hydrogen do? Makes our oxygen positive. Does oxygen want to be positive? No. So it starts to draw electron density away from where? The pi bond. What's the problem with drawing electrons away from the pi bond? Our carbon becomes more positive, which makes it more electrophilic, so it needs to react with a nucleophile. Do we have a nucleophile? Yeah, we've got our nitrogen. Okay? So we've got our first attack. So the intent is find the chemistry, see if we can balance out our charges within the structure. If that starts to push charge around, then start to go outside and see what can happen. Okay? Why do we not start with our oxygen being electrophilic? It is formally positive after all. Why did we not just say the nitrogen attacks the oxygen? Why can't it form more bonds? You're right. How many electrons are currently around the oxygen? 8. Can oxygen exceed its octet? No. So while oxygen may be formally positive, it is not the electrophile because it can't possibly accept more electrons. Okay? So this is where it gets fun. And by fun, I mean very, very tedious. I'm going to try my best to draw these out. Okay? So we'll draw exactly what our arrows show. Nitrogen, hydrogen. You'll notice as well that I did not specify what the bonds were on the nitrogen. Any ideas why? Because I'm going to use this mechanism to represent both the primary and secondary amines reacting with carbonyls. So we'll go back through and change those hanging bonds. Instead of being implied carbons, we'll alternate between hydrogens and carbons, try to see what the end results are. So we've now shown the electron pushing. What happened to our structures? Is this our answer? What's wrong with it? Nitrogen needs to be formally positive. Okay. Does nitrogen want to be positive? Oh, bad position. Nope. So what's it going to do? Take electrons from its easiest source. One source is from the carbon bond that we just made, but then that takes us in the reverse reaction. So this is one of the kind of good things and bad things with this reaction, is that they are in equilibrium. So we could see the reverse reaction occur. Is there another place that nitrogen could steal electrons from? Hydrogen. Could take it from the hydrogen. Why is the hydrogen a reasonable option? Why is it an easy bond to break? If anything, you might say it's under acidic conditions, so it wouldn't break. It's probably one of the more polar bonds. Nitrogen is much more electronegative than hydrogen, particularly in comparison to, say, the carbon. So we could see that hydrogen being relatively acidic and being pulled off. Here's the first complaint that I usually get with this mechanism. What pulled off the hydrogen? Some base, okay? Which is a good answer. I like that answer. Okay? Which base, though? Doesn't really matter. Okay? So we would have to go back and look at our solution and say, what's the most basic atom present? And this is where sapling will bite a lot of you when looking at these mechanisms. Okay? Is trying to identify the specifics of what base that is. So let's go back to our starting materials. What is the most basic atom in our starting material? Okay, there's two basic atoms. Highlight them in blue. We're looking at our oxygen with its lone pair, and we're looking at our nitrogen with a lone pair. Which atom is more basic? Nitrogen is more basic because less electronegative than our oxygen. So if we really wanted to get nitpicky and say what is removing that hydrogen, we could go through and say it was another nitrogen or another amine floating through the solution. Okay? That would be our best option as far as this went, okay? As far as the information specified here. When it comes to sapling and trying to evaluate those, there may be concentration issues to evaluate. In most cases, sapling and even your ACS test or even the test that I'll give you are going to be based on the chemistry, not on concentration issues. If you have a question about what I mean by concentration, talk to me after class or in lab and we can go through and look at that. Okay? But for the most part, we're concerned about the chemistry. Is it all that important to specify what that base is? Why not? All we're looking at is removing that hydrogen. As long as there's something basic there, we can remove that hydrogen. We don't care. Okay? Our primary product is the thing with the ring. We don't care about anything else. Is there a question there? No. Okay. So we now have our first intermediate. Okay? Is this structure stable? At least at a first pass. Yeah, why? Everything's neutral. You said no, why? I think you said no.
Because you're going to have the H plus around, so you're going to have protonating oxygen.
We still have H plus floating around in solution. And what I would argue is more important to look at is actually our carbon. Okay? Our carbon initially reacted to begin with because it was very electrophilic. Why was it electrophilic? It had an electronegative oxygen withdrawing electron density from it. If we now look at our intermediate, do we still have an oxygen withdrawing electron density? Yeah. We also have a nitrogen also withdrawing electron density. So that carbon is still very, very unstable. Okay? Even though it may be formally neutral, it still has the potential to react. Okay? Yeah.
So we can't really say that it's stabilized by Hedger's, kind of? Since
Not really. Yeah. This is effectively your hemiacetal. Okay? And remember, your hemiacetals, depending on equilibrium dynamics, would go either to the complete acetal or all the way back to the carbonyl. And that's kind of where we're sitting at, the hemiacetal equivalent. Okay? So there are things that we could do to keep it somewhat stable, but it's not the most stable under these circumstances. Okay? So we could now try and come up with ways to stabilize that carbon. If we had another atom come in, we'd have to break one of those bonds. Okay? Add another nucleophile. So instead of looking for another nucleophile, let's look for a nucleophile within the structure. Is there another nucleophilic atom within that structure? Okay, oxygen, why oxygen? That doesn't make it a nucleophile.
It's part of the carbonyl part. It's part of the carbonyl.
True, but why does that make the oxygen nucleophilic? You're right, it is nucleophilic. I want to know the reason why. Why does any atom become nucleophilic? What does it need to do? Donate electrons. Why is the oxygen nucleophilic? It has electrons. Okay? Is there another atom that has electrons? The nitrogen. Between the nitrogen and the oxygen, which one's more nucleophilic? The nitrogen is more nucleophilic. Okay? So what we could go through and do is find our second nucleophile within the structure and say the electrons from our nitrogen come down. Don't draw that. Okay, I've got the benefit of backup. Okay? Now we have too many bonds, and we could now break the bond to our oxygen. Why did I say not to draw that? OH minus is an awful leaving group. So that is not going to leave on its own. Okay? So what do we need to do to help facilitate that step? We need to protonate the oxygen. Okay? So we can put in our H+, and our oxygen can share its electrons with H+. Where did the H+ come from? From the solution. Another good answer. It came from something that was remotely acidic. Okay? So again, that same issue. I don't care what it is as long as it supplies hydrogens. Draw in our... Oops, thank you. You're right. Oh, that's not an eraser. Did I already get rid of my hydrogen? Yeah. Okay. Is there anything wrong with this structure? Oxygen needs to be formally positive. Does oxygen want to be positive? No. What can it do? It can take electrons. Where can it get those electrons from? Carbon or hydrogen. If it takes from the hydrogen, we go backwards. If it takes from the carbon, what happens?
It leaves carbon strongly positive.
Trying to space this. Well, let's just see what happens. We have our nitrogen, those two unspecified bonds, and we have water as our leaving group. And since you already specified it, we have the positive charge on that carbon now. Does carbon want to be positive? No. Is that a stable carbocation, first off? Yes. Why is it a stable carbocation? It's what we've been specifying as 2+. I can't believe that's stuck. We're looking at a tertiary or a 2+ carbocation. Okay, so that is relatively stable. Okay, how can we stabilize it further? We can take the lone pair from the nitrogen and share downwards. What's the result? Cool, I did actually space this correctly. Maybe. That's too big. Okay. What's missing? Positive nitrogen. What's the relationship between these last two structures? They are the same thing, so what arrow should we show? I think I heard that mumbled. Needs to be a resonance arrow. Okay. Here's where we see a divergence between our primary versus our secondary amines. If this is a primary amine, what happens? That nitrogen has an extra hydrogen. So this is our primary path. How does that change our end result? Does nitrogen want to be positive? Nope. So what does it do? Takes the electrons away from the hydrogen. What atom picked up that hydrogen? Some base. What base? Who cares? Good. I like that answer too. Okay. Oh man, can't draw that nitrogen. It's a little bit better. And we now have our primary nitrogen result. This species is commonly referred to as a couple different names. First we get the imine. It's a bit sloppy. And it's also known as a Schiff base. Why do we call it Schiff? That's not how you spell Schiff. It's some guy's last name, exactly right. Actually, I don't know how to spell Schiff either. That looks a little bit better. So Schiff is some guy's last name. Why is it basic? We have a lone pair on the nitrogen, which by definition makes it basic. What makes it even more basic than, say, just a standard nitrogen? We could do resonance stabilization. We could have that pi electrons come up to the nitrogen, further stabilize our protonated structure or our conjugate acid. Okay? So this is a very synthetically useful species when we're looking at reactivity. In particular, it has massive implications in biochemistry. Okay? A lot of biochemical pathways utilize Schiff bases. So you can take the nitrogen from, how many of you know you guys probably know your amino acids better than I do. What's a nitrogen-containing amino acid? Any of them? Yeah. How about the one with the nitrogens at the end? The two nitrogens. Positive I'm remembering this amino acid right, but I could be wrong. This guy? Isn't that one? Okay, fine. Whatever. Got another semester to worry about memorizing those. Okay. You're looking at potential amino acids. I think it's aspartame, something like that. That nitrogen can react with a carbonyl to form a Schiff base, which is then reversible. The reversible chemistry helps us go backwards as well as forwards, and so we could put on our amino acids to react, cause our substrate to change its structure temporarily, and change the chemistry. We can then do whatever biological reaction we wanted to do, and then kick off the amino acid at a later step. Okay? So your Schiff bases are really, really important in that respect. Okay? So what happens if it's secondary? Okay, so here's where I get the benefit of an eraser. Now it's no longer a hydrogen. Now I'm saying I've got carbons out here. And I don't care how many carbons, so I'm just going to leave them as carbons. Does our nitrogen want to be positive? No. So it's going to start to steal electrons. Where would it steal them from preferentially? The pi bond. But what's the issue with that? We get a carbocation. So that carbocation doesn't want to be positive either. Okay? How can we stabilize that carbocation? We can take a hydrogen off of a proximal carbon. We get our nitrogen back to being happy, and we form this structure, known as the ene for You're right. Let's back that carbon away. I tried to pick the smaller ring so I didn't take up as much space. Ene for alkene, because we have that carbon-carbon double bond, and amine because, well, we have an amine. So we have the enamine. Also another useful structure to work with, okay? Which becomes more important when we move into chapter 2, or 22. So this enamine structure plays a huge role in chapter 2, or plays a larger role in chapter 22. Okay? Questions about those, or that mechanism? The 1, 2, 3, 4, 5 steps. So actually, all in all, that one's not too bad. Okay? Evaluate each step of your reaction, do only what your arrows show, and make sure your arrows are moving the correct direction. Okay? It takes some practice, but it'll help you get through it. The reason why I emphasize mechanisms is that when you get into the ACS test and if you see something that you haven't seen before and you answer all your other questions, you can come back to it and start to evaluate positives and negatives, start to shuttle those around and see what happens. Maybe you can actually get the answer without having ever seen that material before. Okay? Questions about that? Okay. So where we push from that is what other amines we can use. We can use hydrazine or N2H4. That will react just like we just looked at. Right? And we form, it's not officially an imine, but it's very similar to it. For it to be an imine, this NH2 has to be a carbon. Okay. So what's special about this is in the formation of that product, we now have a very favorable situation. We have something that starts to approximate N2. Why is that important? N2 is a gas, extremely stable. What makes it even cooler is being a gas, as soon as it's formed, it is now completely removed from the reaction. Can we reverse a reaction if we don't have one of the reactants? No. So we can go through and remove that nitrogen structure in a process known as the Wolff-Kishner or Kishner reduction. So we start off by reacting with hydrazine to form that NH2 or the N2 complex. We can then add a base. That base is going to facilitate the removal of the acidic hydrogens. Okay, what acidic hydrogens do we have? It's a bit odd. We don't really have any superacidic hydrogens. Okay, what's our potentially most acidic hydrogen? Either nitrogen to hydrogen, whoops, that's not a carbon, or our carbon to hydrogen. Which one's more acidic? The one with the nitrogen, because nitrogen is more electronegative than carbon. We would expect it to take the electrons preferentially from hydrogen. Taken a step further, we have resonance stabilization. We could take those electrons and start to donate them towards the other nitrogen. Okay? We can continue this process until we effectively form nitrogen gas that is now very weakly held to the structure. That nitrogen gas can be freed from the structure with some more acid-base steps, and we end up doing a complete reduction of the carbonyl. Okay? And we end up having just our standard alkane in this case. Okay? Questions about that real briefly? Okay. Oh, shucks. Apparently I decided that I was going to draw it out. Okay, so we are going to go ahead and start with our imine-like structure. What did we have? A cyclohexane? Keep those in black. Our base comes along. OH minus, what is it going to do? Take a hydrogen off. Where do those electrons go in that nitrogen-hydrogen bond? We could take them to the nitrogen, or let's push it a little bit further. Let's move it to forming a pi bond. What happens? Good. Questions about what are shown? Is that what we've got? This is again one you probably don't want to draw out, at least not in pen. Somebody have any issues with that structure? There is a charge, but there's another issue with it. What's that? What's going on with our center nitrogen? Has too many electrons in general. So if we're going to take our electrons where we had before, take our electrons and shift them into forming a pi bond, what do we need to do? We're going to have to break this pi bond and put those electrons onto our carbon. Okay? Is a carbanion particularly stable? No. So what we would probably see in this case is a very strong reverse reaction. But let's push it a little bit further and see what else could potentially happen. What can we do with that carbanion? Is it nucleophilic or basic? In this case, it is actually only one. For it to act as a nucleophile, what does it need to react with? Anything other than hydrogen. Okay, we're looking at a tertiary carbanion. Really, really unstable. Also extremely sterically blocked. Would we expect it to act as a nucleophile? No. So it's going to preferentially act as a base. So we could have it pick up a hydrogen. Cool, what's the result of that? Do we have that incredibly unstable carbanion anymore? No. Okay, there's our hydrogen. So that's cool, we've now somewhat stabilized it. Okay. Still not the most stable of structures, and we still have a lot of base floating around in solution. Do we have anything remotely acidic? Just as before, we still have that hydrogen. What can happen? We can again go to form a new pi bond. How many bonds would then be around our nitrogen? Or how many electrons would be around it? So what do we have to do? Break a bond, put our electrons onto that carbon. What's our result? We have our carbanion. We have our nitrogen gas. Generated water again. Is our carbanion stable? It's again basic. We push to our end result. Oof, that's an ugly looking structure. Our fully reduced alkane or carbonyl. Okay. Why can we form the carbanion if it's unstable? It has to do with the loss of that nitrogen. Okay. If we kick off nitrogen gas, we've now made something incredibly stable to offset our unstable carbanion. Okay. So if given enough time and heat, we can actually push this reaction to release that nitrogen gas, and we've done our full reduction. Okay, so this reaction hinges on the formation of nitrogen gas. Without that gas, we really don't see a favorable reaction. Okay, questions about it? Okay. So alternatives, we could go through and do a thiol reaction. Remember how we briefly talked about reacting sulfurs? In this case, we have a dithiol. The dithiol is going to react very similarly to the diol. We end up generating, as an intermediate, which I don't really have any space to draw it, the equivalent of if it had been a diol. That species can then be reduced using Raney nickel, okay, which we've seen before. Okay? So it is an alternative to going through and doing the Wolff-Kitchener reduction. We could also use the Clemenson reduction, which we saw back with, I think, EAS chemistry, using the zinc, mercury, and HCl with heat to go through and reduce the acetal group into an alkyl or an alkane group. Okay? We could also go through and use hydrogen and palladium. So why would we use one over the other? Kind of has to do with the conditions. Okay? If we had a very acidic functional group, is the Wolff-Kitchener reduction a good option? Why not? Yeah. Wolff-Kitchener required a strong base. If we had an acidic functional group, the acidic functional group reacts with a strong base and neutralizes the reagent. We don't get our reaction to occur. If we had a very basic functional group, would we want to use the Clemmensen reduction? Probably not, because one of the reagents needed in the Clemmensen reduction is HCl. So what we'd want to do is evaluate the other functional groups present and decide, are those going to help or are those going to hinder the reaction? So you have to evaluate the structure overall. Are there other weird chemistries going on with it? Okay. Questions about that? Okay. In general, some synthetic strategies. So your textbook likes to go through these. I'm not sure I like their summary version of it, but they've got some reasonable adjustments to look at. So what we want to go through and do is look at what changes either we want to occur or could occur when we're trying to build a reaction. Okay? If we're going to change the carbon-carbon skeleton, we need to add or subtract carbon bonds. Okay? When we're looking at our carbonyl chemistry, we had a few reagents that could add carbons. We could go through and do Grignard reagents with our carbonyl, which we saw a while ago. We could also use a cyanide group. Okay? Put on a cyano. That adds a single carbon atom. Our Grignard could add a whole lot more depending on what our Grignard reagent was. And then the last one that could affect our carbon skeleton is looking at the Wittig reagent, where you generate that ylide structure and you do the carbon-carbon double bond formation. Okay? So trying to piece together what changes occurred can help you start to predict what reagents you need to go through and use. How many different carbons were added? What functionality changed? Okay? The next thing that we could go through and do is look at a change in functional group. Ultimately, we could look at carbon-carbon bond cleavage, which is another way, as far as the textbook is trying to discuss, is actually looking at forming a carbon-oxygen bond. Okay, to do that, we could have gone using the Baeyer-Villiger reaction, okay, to make our ester. So we can see that weird rearrangement. How do we know what group rearranges? In the Baeyer-Villiger, you guys vaguely remember that? Okay, it's the one where we form an ester. So our oxygen comes in and attacks, but then we do a rearrangement. Either our red carbon moves or the other atom moves. Okay, which group moves? In this case, we're looking at a primary shift, or we're looking at a tertiary. You guys vaguely remember that? Why the tertiary? How do you know that? Yeah. It's one of those things you just had to memorize. Okay. I think it goes, was it hydride, tertiary, secondary, phenyl, primary? And then methyl? Okay. Hopefully you won't see that, so hopefully you won't have to have that memorized, at least for the ACS test. I will probably ask one question on that for the exam 3. So just kind of be aware. Okay. The other one that we could look at is the carbon-oxygen bond cleavage. So we could look at the full-on reduction. Sorry, I cropped that kind of awfully, cropped out the functional group. But we could reduce the carbonyl using the Wolff-Kitchener method down to just the standard alkanes. Okay. And we'll look at the non-cropped version here in a second. One of the last things that we could go through and do, which your textbook didn't put in, at least on as far as the slides go, is we could look at temporary changes or protecting groups. So if we used oxygen, okay, so our far right is looking at our oxygen as a nucleophile, we could generate and form our hemiacetals, acetals, or hydrates, where the acetal is now our fully protected carbonyl. Okay, why is it protected? What functional groups do you have in the acetal? kind of. Carbon, oxygen, whoops, carbon, oxygen, carbon structures are ethers. Okay. If we think back to our ether functionality, those are very, very non-reactive. So to form the acetal, what we did was started with a carbonyl, removed the carbonyl chemistry by turning it into a hydrate or a hemiacetal. But our hemiacetal also has that alcohol functionality or reactivity. So what do? We can push that even further to making it effectively a diether. Okay, so now it's fully protected. We've converted something that was super reactive as an electrophile into something that was arguably more reactive, because we now had the acid-base chemistry and all sorts of other fun stuff with the alcohol, and then converted it entirely over to our ether functional groups, okay, which have very minimal reactivity. Okay. The other option is we could have gone through and used nitrogen as a nucleophile. And with our nitrogens, we really only had two options. We could have it react, whoops, I was pretty sure it's supposed to have more information to it. If it was a primary nitrogen initially attacking, we get the imine. If it was a secondary, we get the enamine. Okay. Both of those now go through and change the structure a little bit, change the chemistry. Again, reversible. So just kind of be aware of that. Okay? Questions about all of those?
That last nitrogen has 4 bonds on it.
You're right, I was supposed to remove that hydrogen. You're absolutely right. So I'm going to have to figure out a way to fix that within these slides. Because, yeah, this was, come back here. That was supposed to be kind of your summary slide. This was if you had a primary amine. This was as if you had a secondary. I'm not quite sure how I can fix that so you can see that extra information, but I'll see what I can do. So this slide is part of the show. It's got everything up there. I will probably try and post it as just an image file, just like we did with all the other reactions. All right? Questions about it? And if you see typos within it, please let me know, because I don't want you studying the wrong stuff. All right? Okay. So last things that we can talk about within this chapter, spectroscopy. Your IR analysis, as far as this chapter goes, there's really only one thing that you need to know. You have a strong peak, in case you couldn't tell. You're looking at the carbon-oxygen double bond, and it shows up about 1700. Okay. What if it's a ketone versus an aldehyde? How much does it change? Anybody know?
As far as the carbonyl is concerned?
Yep, as far as seeing that signal at 1700. Carbonyl ketone versus carbonyl aldehyde. Doesn't change it much at all. You're looking at probably 10 to 15 inverse centimeters. So how would you decide which one it was based on the carbonyl stretch? You don't. Okay? Look for that strong, sharp signal at 1700. Leave it at that. You now have a carbonyl. Go somewhere else for your information as far as if it's an aldehyde or a ketone. Or for that matter, a carboxylic acid or an ester, okay, or an amide. All of those have slightly different carbonyl stretch information because you've changed the conjugation, you've changed the electron density around the carbonyl. Okay? All you need to know as far as your IR goes, you see that signal, you have a carbonyl, look elsewhere for the rest of the information. Okay? Questions about your IR? With NMR, really the only, well actually both of these are pretty big. In the carbon NMR, you will see a signal for the carbonyl right about 200. Okay? I think it drops as low as 180, but then goes up to 210 maybe. Okay? So you can look at a carbon NMR and see that signal and go, yep, there's a carbonyl. Okay? That's about all you should do with your carbon NMR. With the HNMR, a carbonyl has how many hydrogens? What does a carbonyl look like? is a carbon-oxygen double bond. How many hydrogens do you see? 0. So when we're looking at HNMR, where do we find out information about carbonyls? We don't. Okay? The only thing that you can pick up is if instead of a carbonyl, you now have what functional group? An aldehyde. The presence of that hydrogen directly attached to the carbonyl carbon now causes a distinctive shift, and that's how you can get a signal about 10 ppms. Okay? That is the only signal that you will pick up as far as hydrogen NMR goes. Okay? I really hate that your textbook and other little summary things do this kind of little diddly thing on the side here. Yes, the methylene, which is this carbon and those hydrogens, are closer to a carbonyl, which causes them to shift, okay, if the carbonyl wasn't there. So we do see this 1 ppm shift. Okay? Great. What else would cause a 1 ppm shift? Being next to a double bond, being next to a halogen, being next to 2 halogens, being next to a double bond and a halogen, being next to an oxygen. There's a billion different things that would cause that shift into that range, which means don't analyze it because you don't know that information yet. Okay? Chemical shift should be a very quick interpretation. Use the rest of the spectroscopy to help you finalize what that structural piece of information is. So memorizing that a carbonyl will shift you into that 2.2 ppm range is at best misleading, at worst offensive, actually. I don't think you should ever be exposed to it in that respect. Okay? Questions about spectroscopy? Okay. These are all labeled out for you. Let's use some of our information to pick up what we would expect. For the structure, they're both the same, so let's just pick one. What would we expect to see in the IR? Okay, I'm going to give you a hard time for saying a carboxylic acid peak. I'll tell you that right now. And not just because it's not there. How many bonds are in a carboxylic acid? You've got 3 different types of bonds. This OH shows up centered about 3,000. This carbonyl shows up about 1,700. This carbon-oxygen shows up about 1,100. So when you tell me there's a carboxylic acid peak, and I'm not trying to pick you out in general. This is something that instructors, I've seen people that teach spectroscopy go through and say it's a carboxylic acid peak. It pisses me off. So it's not you, it's the way you were taught it. Okay? And I won't name names, even though you are. Okay? If we go through and take a look at the IR, what do we expect to see? We have carbon-oxygen double bonds. We would expect something about 1,700. Would we expect just one signal at that range? This one's a little bit trickier. Okay. So for sure, this guy, I would say it's actually probably going to be about 1,710. Okay. Most carbonyls shift a little bit higher than 1,700. This one over here is a little bit different. Why? Oh, I didn't even see that. It's an aldehyde versus a ketone. So it does cause it to shift a little bit. Okay, there's another reason why it's different. Why is that double bond affected? There's a resonance effect. There's conjugation between the carbon double bond and the carbon-oxygen double bond. That causes that signal to shift to lower frequencies. Okay? So we might expect something in the 1650 range for that. Okay? So we would probably expect 2 signals for the carbonyl. As far as their intensities, carbonyl is always going to be intense because it's extremely polar. Beyond that, I wouldn't expect you to know much else. Okay, so you might take a stab and say, yes, there's 2 carbonyl, or 2 peaks in that range, because we have 2 distinctly different types of carbon-oxygen double bonds. All right? After IR, we've got carbon NMR. What do we expect to see for carbon NMR? Where should this carbon show up? Carbon E. Show up about 200 ppms. How about the other one? You're looking again about 200. Okay? So what we're trying to do is just simplify and guess at what we would see. Would we expect them to show up on top of each other? No. Why should they be slightly off? Same reason as IR. They're slightly different carbonyls. Those carbons are feeling a slightly different environment. We're going to see a slightly different chemical shift. When we look at HNMR, based on what we were talking about, in the HNMR, what's the only signal that we would see based on what we were talking about? HC is the only kind of important one. Why only look at that one? Because we talked about these in the EEAS chapter. Was that chapter 18 or 19? Okay. So if you want help figuring those out, go back to chapter 18 or 19 or talk to me after class. HC is the only one that's going to stand out as slightly different, and that one we would expect to show up about 10 ppms. Okay. So with carbonyls, it's kind of nice because you can see some very characteristic information. If you have that aldehyde, you will have a very characteristic signal at the 10 ppm range. You've now identified that there's an aldehyde in your structure. You could probably eliminate some answers. Anything that has a ketone, just a ketone in it, can't be your answer. Okay? Questions about your spectroscopy? If you download the slides, that box is just a drawn-in box over the top. Actually, I think I just did this. You have the answers underneath it, right? Yeah. Okay. So I don't need to explain that box. Never mind. Nomenclature. How are you guys doing with the nomenclature? Looking at the book. Yeah. I was just asking to see how you were doing with it. Our aldehydes, we'll get the AL ending, so you get the al, so you replace the E of your ane, ene, or ein, and turn it into an al. Make sure that you include the aldehyde in your parent chain, so that if we go through, not quite sure why the book did this either, we would not number this structure as the octane, even though that's the longest carbon chain. And the reason we don't number it that way is because we have to include our aldehyde. Okay? If for some reason you can't include the aldehyde in it, which means you have a higher priority functional group, I'm going to take a stab at this one. Since it's not in the slides, you probably don't have to worry about it. If we put in a carboxylic acid, that is a higher functional group than our aldehyde. How would we name where our aldehyde is located? First off, what position is it at? 2, 3. It's the same both directions? No. So we name it 4 because we're starting from our higher priority carboxylic acid. So in this case, we would have octanoic acid, but at the 4 position, we have this aldehyde. If we just said 4, one other thing that we could go through and add here, we can specify an aldehyde at the end of a chain by referring to it as an oxo. Okay, so we could go through and say it's 4-oxo octanoic acid. Problem with that is that oxo is also the name given to a ketone. So if we say 4-oxo, we're not specifying that extra carbon. What we're saying is that there is a carbonyl at that position. So how do we specify that there's an aldehyde there? Not a particularly fun name. You'd refer to it as a carbaldehyde. So you get 4-carbaldehyde octanoic acid. Okay? Just be kind of aware you might see that name float around. I don't think I saw it in the textbook, and it's most certainly not mentioned in the slides. Okay? So you may or may not encounter that. Just want to give you the heads up. Okay? So with our aldehydes, and now actually ultimately ketones, I made sure to include again our priority of naming. Our carboxylic acids are our highest priority, and we go aldehydes, ketones, alcohols, and all that other fun stuff. Okay? The arrow is to show if it is the highest priority group, that's what we name it based on. If there's another group of higher priority, that's when you shift to naming it as a substituent. And I know I said oxo there, but that one's wrong for the aldehyde. Kind of wrong for the aldehyde. How is it kind of wrong? If we looked at that acid structure, oh, that was terrible. Okay. Yes, this gives us our acid name, and God knows how many carbons are in there. We could still refer to this one as an oxo and just use the last number. We can get away with that because the carbon of the aldehyde is part of the main chain. So we can refer to it as the oxo. So your aldehydes can become very, very tricky when it comes to naming. If they're part of the main chain but not the highest priority group, we can go with oxo. If they're not part of the chain, they get a new naming system. And I'm pretty sure that's the carbaldehyde. Oops. Okay. Any ideas why that might not show up very often? What's that? That's probably a good one. It's annoying. It's also one of the highest priority functional groups. Okay? There's not a lot of different options that can go higher functionality. Okay? So you probably won't have to worry about that. So we again can go through and look at a couple of these. Let's look at the bottom two. I think they're both the same. Yep. Which numbering is correct for the bottom two? Left or right? Why should the left one be correct?
It says correct.
Okay, well now you got to come up with a reason why it says correct.
Because the aldehyde is a higher priority than.
The aldehyde is a higher priority than the alcohol and the alkene. We'll name it based off of the aldehyde's priority. So your aldehydes will always get specified or always be at position number 1, which is also nice because now we don't have to specify that they're at position number 1. Okay? With the exception being if we had a dialdehyde, because then we'd have one at the beginning and one at the end. Okay? So the correct numbering is here. It's this guy. So we could call this structure, based on the 7 carbons, heptanal. What substituents do we have? Whoops, I did that one wrong. Why is heptanal wrong? Heptenal, because we have the double bond. We're then going to have to specify where that ene was. So hept 6-enal. And then we also have the alcohol and the methyl group. How do we name our alcohol? 5-hydroxy. If we go back up to the substituent things, remember, that little red table is actually pretty helpful. This one becomes 5-methyl. How do we specify we have a ketone? Can't call it now. And there's no point calling it an oxo if it's the only thing there. We'll change our ending to the own ending. So our other structure, again, 7-membered or 7 carbons. So hept. This time it's all sp3, so we can get away with the an, the own ending. Where do we specify that the ketone is located? We could do 3-heptanone, or we can do heptan 3-one. Both are valid. Questions on your nomenclature? Thank goodness.
Priority's just something that
Yep. All your nomenclature is someone sat down and said, these are the rules, everybody follow them. Okay? So another textbook summary of what was going on in another compound. Do you guys want to do that other compound? I'm going to take that as a no, because I don't want to name it. Okay. Questions in general about chapter 20? Because this is now 22. Okay. So there have been several requests to start the lectures off with what the reactions are in total. I'm working my best to go through and get all of the reactions summarized. This is not all of them for 22. And 22 is a bit weird because you look at a type of reaction and then a whole bunch of named reactions as well. Okay? Ultimately, what 22 is driving at is that while we have a carbonyl, okay, that's not the only chemistry. So when we look at a carbonyl, we addressed this already. We have the electrophilic carbon, and we said that was really the primary driving force of our carbonyl, was that electrophilic carbon. Though we did also have the basic nitrogen up top, the Bronsted-Lowry basic, that's an oxygen, up top. What 22 comes along and says is that actually it's not just those two positions. That oxygen is now so electronegative, and that carbon has now become more electronegative because we've changed its hybridization. It's become less hybridized because it went from an sp3 to an sp2, so it has more S character. That electronegativity has increased so much that it now actually starts to draw electrons away from our neighboring carbons. Well, if those carbons start to lose electrons, what do they start to do? Try and reach out for another electron source. They take those electrons from hydrogens attached to them. Which means when we look at the carbonyl, or the acarbonyl functional group, not only do we have an electrophilic carbon, a Bronsted-Lowry basic oxygen, but we also have a Bronsted-Lowry acidic hydrogen. Okay. On its own, that's not that big of a deal. What happens, though, if we remove that hydrogen? Okay, to me, it's a little bit easier looking at the enolate. What changes about our structure? What happened to our oxygen? It's now formally negative. What's the issue with a negative oxygen? Not particularly stable, becomes much more reactive. We now have a much more reactive Bronsted-Lowry base. Okay? It's taken a step further now from our original carbonyl. Our carbonyl at least had everything nice and stabilized. So our oxygen can now be both basic and nucleophilic. So we started with a carbonyl that had mainly just electrophilic reactivity. And now a small change in the structure has all of a sudden made our oxygen now nucleophilic. There's a larger, more important issue with this. Can you draw a resonance structure for that enolate? And unfortunately, I'm going to draw this on the board, but we'll see it on later slides. Whoops. Can I stabilize that negative oxygen? How?
By shifting the
Shift the electrons down. What's that? No, you're right. How many bonds does this carbon now have?
or some pi bonds in the carbon on the way.
And what we now have is that structure. What's interesting about that structure? Highly reactive. How is it highly reactive? I think you said. We've now made our carbon extremely nucleophilic. Okay? So a small change in where our hydrogen is located has now converted a carbonyl to being an electrophile to now turning that structure into a nucleophile. So all of the chemistry that we're looking at in chapter 22 is now taking the carbonyl compound and looking at how it can react as a nucleophile. Okay? So we're going to look at some standard things that we've already seen. And by some, I think it's just really one. We're going to look at bromine acting as an electrophile and what happens when it reacts as an electrophile. But there's another big electrophile that you guys should all now be super, super aware of. What is that other electrophile? Carbonyls. If I remove that hydrogen, I now have a very nucleophilic carbon. That nucleophilic carbon, to generate that, came from our starting ketone. How does our starting ketone react? As an electrophile. So depending on how much of that enolate I form, I could potentially have that same enolate react with the carbonyl, okay, on a second molecule. Okay? And that's where you're getting your aldol and your Claisen reactions as far as this chart goes, the bottom half. So the top half, we've got our bromine, and then we also have carbons. Why did I write nucleophiles? Carbons as our electrophiles. How do we generate an electrophilic carbon? What charge does a carbon need to be if it's electrophilic? Positive. How can I get a carbon to be electrophilic without adding too much other chemistry? What does it need to be attached to? If it's attached to a metal, what's the difference in electronegativity between a metal and a non-metal? It's big in favor of the non-metal, which means the non-metal becomes nucleophilic, not positive, becomes negative. Okay. What else could we potentially attach it to? Whatever that atom is needs to be able to do what? It needs to remove electrons from the carbon. What atom removes electrons from carbon? What's that? Halogens. We're looking at any kind of halogen. Okay. So to generate our carbon electrophiles, so there's yet another typo. We'll have to go through and fix that. That should say electrophile. That says electrophile. Okay. So these are kind of the overall reactions that we're going to be working with and how we end up manipulating and generating each of these. Okay. Within the boxes are kind of the primary examples or the major example of each of these types of reactions. Outside of the boxes, we're looking at kind of the overall reactions. Okay. More generic examples. Okay. So for instance, with the bromine reaction, we just do our standard nucleophile, electrophile, and we generate our product with the bromine on it. If we propagate that chemistry to more specific examples, we can go through and do what's known as the haloform reaction. We can convert a methyl ketone. It's methyl because there's a CH3 next to the ketone into a carboxylic acid. Okay? Or we could run, I don't know why this one gets its own special name, but it does. Can do the Hell-Volhard-Zielinski reaction, which is effectively the same thing as our bromine electrophiles, except our carbonyl is a little bit odd. What makes our carbonyl odd? What makes that carbonyl interesting or different? It's next to the OH, so we're looking at a carboxylic acid carbonyl. Okay. In the presence of bromine, we wouldn't expect this reaction to go, except we can push it by adding in some other pieces. Okay.
So should we look over 21 a little bit?
We're going to skip 21 for the moment. We're going to come back to 21. Okay. What I wanted to go through and do was cover carbonyl chemistry in general with our ketones, and now the enols and enolates. That's really where it's important. 21 is just looking at carboxylic acids. Okay. Which will be nice, because we'll end the semester then with acids and bases, because the other thing we got to look at is amines, which act primarily as bases. Okay. Questions about anything that's up there? I know, we haven't talked about any of it yet. Does this look as good as I could possibly get it? Do you have suggestions on how I should change it? Maybe we should go through it a little bit and see how bad it is. Okay. Like I said, it's not done yet. I still have 2 more sets of reactions to go through and do. So our alpha carbon chemistry, so enols and enolates. When we look at chapter 20, it was all about the electrophilic properties of our carbonyl. 22 now says let's look 1 bond further away and see how the carbonyl affects that chemistry. So that 1 bond further away we could refer to in different fashions. In this case, we're going to refer to it based on the locations. And they came up with the Greek system, alpha, beta, gamma, delta. What we're concerned about right now is that alpha carbon's chemistry, and in particular, the acidity of the hydrogen at that alpha carbon. Okay? How much further do I want to get? This might be where I wanted to get. Okay? What we're looking at is our enol and enolates. We've seen these before. When you take a look at the alkyne reacting in the presence of sulfuric acid, water, and mercury, what happens? Okay. Our sulfuric acid and water with an alkene remove 1 pi bond and put on an alcohol and a hydrogen. Problem with that structure is that the pi bond is now really close to the oxygen, and we end up seeing what's known as a tautomerization. That tautomerization turns it over into the ketone. Okay? So the acid addition that we would do with a pi bond with an alkene generates that carbonyl. Okay? So we have seen this before, we just weren't trying to take advantage of that chemistry. When we're talking about the chemistry we're going to start with a carbonyl, and under either acidic or basic conditions, we can convert the structure over into either an enol or an enolate. The enolate is going to be the primary driver for all of our reactions. Why would the enolate be our primary driver? We don't have the stability that we see in the enol. We get very similar chemistry in both cases. They both have that nucleophilic carbon through resonance. Okay? But the enolate is kind of the primary driving force. Whereas our enol, to go through and do that, it's already generated a pseudo-stable structure. So to go through and make that carbon nucleophilic gets a bit dicey. Okay? Questions about that? What type of chemistry is performed to go from our keto to our enols? It's acid-base chemistry. It's important because we have that carbon nucleophile. Okay, so what you need to be able to do is see how that carbon nucleophile reacts with a variety of different things. All right. We will pick up there on Wednesday, but first we'll go ahead